Okay, so let's start the next lecture. What we are studying the spontaneous emission problem. So let me remind you what we are doing. We just take some kind of a caricature of an atom. Instead of having infinitely many ground states plus a continuous spectrum, our atom is supposed to have only two states. I will change the notation slightly compared to the lecture notes and last lecture. I will call this fellow 1, this fellow 2, instead of 0 and 1. And this guy will have energy E1, this guy will have energy E2. So this two-level system is now coupled to a whole sea of photon modes of electromagnetic field, and the coupling is taken in the dipole approximation, and not only this, we've also made a simplification which is called rotating wave approximation. Out of 4 terms in the coupling Hamiltonian, we left only 2. And with these simplifications, one can ask what is the evolution of the initial state, which is the excited atom and the photon vacuum. And if I would write, as I did last time, the state vector of this thing is the amplitude, survival amplitude, as sometimes is called, of 2 and vacuum state for the photons, then this fellow, after all these approximations that we have made, is coupled only with unknown coefficient, but is coupled only to the lower state and the single photon of a type lambda. Lambda is a pair of things, so lambda is the same as knowing the wave vector and knowing the polarization, I equal 1, 2, or plus minus. Yes? So lambda defines us all the photon modes. We work with a system in a box. So K's are quantized. Well, N1 and 2 and N3 are the integers. And we found out, as you recall, of course, what I'm repeating a little more than I wanted, just for the benefit of the viewers who most likely lost the last lecture, a very convenient way of solving the Schrödinger equation, resulting Schrödinger equation for alpha and infinitely many betas, is to use the Laplace transform. And in this Laplace transform, one automatically takes into account the initial condition. Initial condition states that alpha of 0 is 1, and all betas of 0 are 0. So the set of equations that we are solving looks like this, where this wiggle means that I'm talking about Laplace transform. Z is a Laplace variable. Now I will also simplify my notation here. I will write omega 2. Well, omega 2 stands, it's actually the same as the energy, except that I decided to swallow H bar to make notation simpler. I sum, here are coupling constants and beta lambda, and infinitely many more equations for beta lambda. Of course, initial condition is 0, so nothing is subtracted here. The non-interacting energy is this 1 plus the energy of the photon, and the coupling is this times A right? So that's a set of algebraic equations. What is very important is the value of a coupling. And this I better look into my notes. So it is correct thing. It's omega lambda divided by 2 epsilon 0 volume, quantization volume, and 8 bar. And, very important thing, transition dipole moment with the scalar product with the polarization vector of the mode. Transition dipole moment, what is it? For completeness, D is electric charge times non-diagonal of diagonal element of the position operator. Okay, now, as I say, this is, and we have done it already, this is easily solved. First, from this fellow, beta lambda is missing. From this fellow, I'm getting, I'm sleeping. So from this fellow, I am computing beta lambda, I'm plugging it here. Then I take alpha on the other side, 1 on this side, and divide, and then I get my alpha in the form of 1 divided by the function of z, which I call the resolvent. And the expression for this resolvent, which we have also derived last time, is z plus I omega 2 plus sum over all the modes g lambda squared divided by z plus I times omega 1 plus omega lambda. So, had we lived in the Laplace domain, we would have explicit expression, but of course we are interested in the inverse Laplace transform, which is 1 over 2 pi I times this contour integral, yes, of e to zt dz divided by h of z. And we know about this contour from the theory of Fourier of Laplace transforms. We know that this contour in the z plane should be going from down all the way up to the right of all the singularities of the integral. And then we said, okay, without any interaction, so if all these g's were 0, then our resolvent is very simple. It is just these first 2 terms. So in the inverse transform, I would have just a single pole at minus I omega 2. Of course, then the inverse is very simple, and we get that alpha of t for g lambda equal to 0 equal e to minus I omega 2 times t, which is of course correct expression without any interaction. And then I said, okay, all these frequencies, even omega 2 minus omega 1, which is the transition frequency, are say 10 to 15 hertz. On the other hand, lifetime is 10 to 8, 10 to, I mean, inverse of 10 to 8, 10 to 9 hertz. So it's like 6 orders of magnitude difference between these internal oscillations and the decay process. So one can then assume safely that excellent approximation is obtained for the inverse transform by just looking at the perturbation of our single pole, which was expressing everything for non-interacting system, and then expand expand this new pole in the power series of the interaction, and this way we've got this Z0, the single pole here, in the form, I hope I have it nicely written, well, first we have to start with this minus I omega 2, and the correction is minus sum over all lambdas z lambda squared divided by I omega lambda minus omega 1. I'm sorry, it's already omega 0. Well, omega 0 is, of course, omega 0 is a transition frequency, omega 2 minus omega 1, plus epsilon, where epsilon is this positive real part transcription for the contour. And then I invoked a well-known formula for the theory of residue, distributions, which goes like this, minus or plus pi delta of x, and if I use it, then my z naught is minus I omega 2, and there are two terms. One is still imaginary, and that comes from this principal value integral, and the other is real. And of course, if we now assume the simplification, namely that for the interacting case, alpha of t is still 1 over 2 pi I times gamma e to zt divided by z minus z naught, then of course the solution is simply, so we are closing the contour on the left, and then the solution is simply value of these things at 0, so it is e to 0t, which means that survival probability, which is alpha of t squared, yes, is simply e to minus gamma t. So this real part of our single pole is really telling us, is determining the lifetime, or so far lifetime, of this excited state. The formula for the gamma, because of this pi here and half here, is 2 pi times sum over g lambda squared times delta function of omega lambda minus omega 0. That is this x equals 0. And now we have summarized more or less what I have said last time, and it's time now to compute this gamma. It's not very difficult. How do I write it? Well, I need my 2 pi, of course. Then I need g squared, which is somewhere. Where is g? Yeah, it's here. Yes. So this is 1 over 2 epsilon 0 h bar and volume. Yes. And now I'm having a summation, and I will now split the summation into summation over case. So here I get omega k, yes, times delta of omega k minus omega naught. And here I want to sum over polarizations, and this I will write in obvious way, epsilon I d times epsilon I dot d. And this last sum has only two terms because there are, as we all remember, there are exactly two polarizations. Good. I would like to erase something, but where is some sponge? Used to be. Ah, yes. Okay. So I want to teach you how to sum over two polarizations. Now, we know what are the properties of polarizations. If we, for given k, this E1 and E2 form some kind of the basis, yes? In other words, if I have the following tensor, A1 ith component times epsilon 1 jth component plus epsilon 2 I component, epsilon 2 j component, what I can say about this matrix ij? Well, I can say certainly that this is symmetric, obvious. Then I can say that it can be built out of k and k only, because there are no other vectors.
What is this epsilon with two indices?
Well, this is first polarization vector, but it's ith component. And first, jth component. Second, ith component. So there are two symmetric tensors that can be built if we only know k vectors. What are they? Well, one of them is, of course, universal. That's delta ij. Yes? Let me put some coefficient here, which I don't know what it is. And the other is ki, kj. To make calculations simpler, it's good to divide it by k squared. That is not, of course, the matrix. And that lets me call it beta. So that's from the tensor, so to say, properties of this summation. This must be a form of this guy. Except that from such a form, I don't know yet what are alpha and beta. Okay, so one thing comes immediately from the fact that k times epsilon, whatever epsilon is, whether it's 1 or 2, is of course equal to 0. So if I now take a scalar product of this fellow with k, then of course I get 0 from this side. What do I get when I take a scalar product of this fellow? Then I get alpha, yes? I get alpha times ki. And what happens if I multiply this fellow by epsilon 1 or 2 j? Then I get 0. I'm sorry. I have done something wrong. certainly 0. Ah, yeah, sorry. I multiply it by kj. Then, of course, from this summation I get ki plus beta, and from this summation, k squared cancels, I also get ki. So what does it mean? It means that alpha is equal to minus beta, yes? So I have reduced my problem to only one constant. Now I know that the whole thing is alpha times delta ij minus ki kj divided by k squared. That is assuring me that this fellow is orthogonal to k. Now what is the next thing? Well, the next thing is to take a trace of this matrix. If I make I equal to j and sum over j, then it's the square length of epsilon, which is 1. And this is also 1. So when I take this trace, if you want, then on the left I will get 2. Here I have alpha. And what do I have here? Well, if I take a trace of this guy, it is 3. Yes? And if I take a trace of this guy, it is 1. Right? So, from this we know that alpha is equal to 1. In other words, our summation with respect, summation that we are after here, when one thing is already done. We know how to sum this fellow, yes? We have to simply do what? We have to, I will rewrite everything here. My 2 will cancel. So then I will get pi divided by epsilon naught h bar times volume, sum over all k's, omega of k times delta omega of k minus omega naught. And now, if I substitute my tensor over there and multiply it in each component by d, then what I will get from the unit matrix, I will get, of course, d squared. Yes? And from the other part, I will get minus d scalar product k squared over k squared. I got rid of the polarization vectors. And now the next stage is twofold. There are two simple observations I want to make now. One is, what? Something wrong?
No, I just...
What?
How we know this equation for epsilons, that it is proportional to this Kronecker delta?
Well, because it's a symmetric tensor which can only depend on k. There's nothing else in this little micro-universe, yes?
Yes.
So the most general symmetric tensor is, of course, ki kj and delta ij.
Yeah.
That's it. Okay, so there are two steps that I want to make. The first step is replacing summation over k by integration over d3k. And you remember from some, I don't know, introductory lecture on solid state physics probably, that it's very simple. You have to take this sort of prescription, yes. Just, it comes from the fact that my case in this finite volume situation have this 2 pi over L coefficient times integers. This is one thing. The next is that, of course, I would prefer to work with omegas only, and that's very easy because we know that omega is equal to kc. So in other words, this integration here amounts to 1 over c cubed times d3 omega. Well, omega is of course still a vector, but already with a length which is a frequency. One more thing. For doing the remaining 3 integrations, it is very simple. If we choose the spherical coordinate system for which z direction will be the same as d. Well, why? Well, because this scalar product d dot k will be then d squared times k squared times cosine theta of that. Yes? So it is very nice. And using this spherical coordinates, then what we will get is I have to take again my pi over epsilon naught times h bar. Now volume cancels. I get 2 pi to the 3rd power here in front of everything. I get c to the 3rd power. And now what do I get? I get, of course, integral over phi angle. Nothing depends on this. So this will be d phi from 0 to 2 pi. Then you are familiar with very useful substitution. If you have this cosine theta, it's best to use psi s cosine theta, and then integral over theta angle turns into integral from -1 to +1 d psi. And what do we have for the d square? I can also take out. What do I have for psi dependence? Well, this is simply 1 minus psi squared. Yes. Psi squared, that's this cosine square from the scalar product. Finally, I have integration from 0 to infinity over d omega. Yes? 1 omega was already in the, you remember, in the coupling, and 2 omegas are from the volume element.
Excuse me, why this 1 minus psi squared?
Because
d psi is already psi.
yes, you know, if I take sine theta, 1 minus cosine square theta, d theta, and integrate from 0 to pi, then upon substituting psi as cosine theta, one gets this.
Okay.
It's
Okay.
believe. Yeah. Okay, so I come back. There is 1 omega from G, and there are 2 omegas from the volume element. So I get omega to the 3rd power. Yes. And delta of omega minus omega naught. Now it's of course trivial to do all this calculation, and then what we get at the very end.
Okay, sorry, I know how from this obtain this, but I don't know where this one comes from. Why
This?
do you integrate over yeah?
Oh, because I have to integrate over d3k. So I chose direction of d for the z direction. And then k is described by length of k and phi and theta angles.
Yes.
And I have to integrate over the whole volume.
Yes.
So I have, as you know, the Jacobian is sine theta times r square, yes? So that's why I have this fellow here.
Yes.
1 minus cosine square is there because I had this d square minus dk square over k square.
Okay. No, it's okay.
Yes? Okay. So I think now it's kind of obvious what the result should be, and the result is really a textbook result that the decay rate gamma for the spontaneous emission is equal to 1 over 3 pi d squared omega naught to the 3rd power divided by c cubed times h bar now you know how to do it, yes, how to obtain this result. Now, if I plugged in some typical situations for low-lying states, then indeed I would get that this gamma is, as it should be, is about 10 to 8 or 10 to 9 hertz. That's fine. It is so excellent. I want to make a small remark concerning this quantity. You know, some people, and a lot of them, are concerned for years now with the study of Rydberg atoms. Yes? Rydberg atoms are those for which n value is huge. Yes, principal quantum number is very large. In some experiments, even in the Bose-Einstein condensate, people were getting as high as 202 n. So these are huge, huge, huge atoms. Yes. Now, if you have such a huge atom, then what is the scale? We know, of course, we know that the radius of such a guy is proportional to the square of this fellow. So radius scales like n squared. Yes. So is, of course, the transition dipole moment, because this is the typical length scale of the problem. Yes. So in other words, this d square here, for Rydberg levels, scales with a principal quantum number like n to the 4th power. Well, that looks like, at first sight, that these transitions among Rydberg levels are very fast, maybe. Not so quick, because there's omega naught here. And if I have circular orbits, then because of the selection rule for L, as probably you still remember from some elementary course, n can change only by 1. If so, then omega naught, which is related, of course, to the difference between energy levels, scales. How does it scale? Each energy level scales, as you remember, as 1 over n squared. So the derivative, so to say, scales like 1 over n cubed. In other words, typical scaling of omega naught for transitions among Rydberg levels scales like n to -3. What is the result for the scaling of this fellow? It's very nice, because d squared, as we said, goes like n to the 4th power. And here is 3rd power, so this goes like n to the 9th power. In other words, this gamma scales like 1 over n to the 5th power. And that's really amazing. What does it mean? It means that such states, even though they look you think they are very fragile, are actually incredibly sturdy. These guys live for a long time, unless, of course, touched by someone, yes? Of course, they are sensitive to scattering with other atoms and so on, something that we, of course, did not account for. But had we have such a guy in vacuum, this n equal 100 or n equal 200 states would live for a large fraction of a single second. Completely different order of magnitude than typical dipole transition between low-lying states. Yes. I think that was a remark worth making, even though it is not really directly related to what I'm mostly discussing. Now, I was omitting in this so far a bit of a discussion of this delta, of this collection that is imaginary, so it adds up nicely with omega naught, with the transition frequency.
So,
yes?
Is it the reason that for what we can assume that our atom has only 2 levels, right?
Well, let me put it this way. I did not make this estimate for any Rydberg state. I did it for circular Rydberg orbit, where L is the largest. Yes. As you remember, for hydrogen atom, L cannot be larger than N. Yes. So if I have this orbit, which is like this, then the only dipole allowed transition, which means delta L equal 1, is to N minus 1 orbit, because this is the only state that has such a huge L. And that's my estimate. If I have very elongated state, then it also gets stabilized as N grows, but not with such a beautiful fixed power. It's, as it happens, I don't want to go into detail, it falls off like 1 over N cubed, but still getting longer and longer lived. There are some labs where they are specialists at pumping angular momentum to the Rydberg level so much that it goes to the circular orbit. And Serge Haroche at École Normale, the guy who got a Nobel Prize for very precise measurements, is able to produce such states on demand, so to say, and send them one by one to the cavity and look at the interaction. Okay, so I go back to my delta. I already mentioned last week that it's in some sense a caricature of a lamp shift. The expression that we get for this fellow, apart from the sign, which I don't want to discuss now, I don't remember, but I should look for into the notes whether it's plus or minus, but it is basically this principal value of the integral of G lambda squared divided by omega lambda minus omega naught. So that's the integral. What does it mean, principal value? Well, of course, omegas start from 0 and go to, and of course this should be summed over everything. So it is again integration over all k's and summation over polarizations. I don't want to go that much into detail, but I just want to stress two things. One is, what is this principal value? Let me remind you. This fellow has this singularity when omega lambda hits omega naught. And what is this prescription? Well, this is, of course, in the vicinity of omega naught. Our integrand, whatever is this behavior on omega lambda, this is just proportional to omega lambda, by the way. So this fellow is having something like this. Yes, it is changing sign at omega naught. Yeah? So what is principal value? This is the following prescription. We integrate until this point. We integrate from this point. In other words, we cut this little interval, and then make sure that this is equal to this, and then go simultaneously to 0 symmetrically. Yes, that's the definition of the principal value. And that is fine. This makes this integral, because of this singularity, finite. There is no problem. However, there is a big problem for omega lambda going to infinity. Why? Because the object like this, you remember we had 1 omega here, and 2 omegas would be again from the spherical coordinate. Then integrand integrated over d omega would have omega to the 3rd power, like before, now divided by 1 omega minus omega naught in the denominator. What does it mean? It means that if I would like to cut my integration at some very high cutoff lambda, then for very large omegas, I will get integral of omega squared, which means that this lambda would be to the 3rd power. That's really the divergent integral. And badly divergent because it goes like 3rd power of the cutoff in frequency. Well, one simple term to be reminded is the ultraviolet catastrophe here. Okay, there are many reasons, and I enumerated them here so I will not forget all of them. Where do I have it? I have it somewhere. invent. No, I don't have it. Fantastic. Okay, so there are many reasons why this is wrong. Look, we are integrating over all omegas here. We are asked to integrate over all omegas here. So first, RWA, which was based on the fact that my photon fits more or less the distance, energetic distance between my two levels, of course is wrong for this quantity. Second, since I am integrating here over all omegas, in particular I integrate over very high omegas, then my dipole approximation breaks down eventually. You remember when I was computing gamma, that was very neat because there was this delta function, so omegas that were really important were in the small vicinity of, with a delta, Dirac delta just exactly at the resonant frequency, for which of course I've assumed dipole approximation was okay. So the other sin that we committed is a dipole approximation. What else have we done? Well, certainly we have non-relativistic theory of atom. We are not thinking in terms of Dirac equation and stuff. That is still not enough. I don't remember. I had 5 points. You have notes, yes. The last thing is that we did not do the normalization.
We assume only 2 levels.
Yes, excellent. That would be 5. 4 would be only 2 levels. Again, why it is bad for the so-called clamp shift? Well, it's bad because we assume 2 levels just because we said, okay, we are looking at this fitting photon frequency. Here we need to consider all frequencies, so there were also frequencies that fit some other transitions. So that's another thing. And finally, the normalization. And what is the normalization, let me tell you. You see, when I'm thinking of true relativistic quantum electrodynamics, then there is this notion of bare mass and bare charge. When we write the Hamiltonian interaction star, this, that, Dirac quantized field, then the input parameters, namely precisely these two, mass and the charge, we don't know what they are, we are putting them in. But then, one can define operationally within the perturbation expansion in the relativistic QED, operationally the notion of the mass. I don't want to go into detail. And this notion of the mass computed is of course related to the bare mass by some complicated, crazy power series expansion, which is actually divergent. So in other words, the relation between the bare mass and dressed mass, as people say, cannot be accessed, cannot be computed. But one can replace everywhere bare mass by the dressed mass and bare charge by the dressed charge. And after this is done, that swallows all the remaining infinities. And only this way one gets the lamp shift in the form that can be compared to the experiment, and it works beautifully. Again, depending on how precise the calculation is, to what order of perturbation and so on. And actually, in Warsaw, we have one of these world experts on computing such things to a very high accuracy. Of course, I have in mind Pachucki. But we are certainly not heading in his direction. If someone is interested in these incredibly complicated calculations, you should attend his lectures. But while this delta is small, if it is done properly, then function at the origin, at the nucleus. Now, as you probably remember, only S states have non-zero value at 0. All the other states vanish. So within such approximation in which lamp shift is proportional to the value of the wave function at the origin, only S states are shifted. So now, if I take the standard non-relativistic hydrogen atom, then what we know is that, of course, there is this degeneracy with respect to L. So N equal 2 state has given energy, 1/4, by the way, of the binding energy, both for L equals 0 and for L equal 1, both for S state and for P state. Now, S state gets shifted by the interaction with vacuum field. And the shift, this particular shift is really called the lamp shift. It's been computed for the first time, not very precisely, by Hans Bethe in 1947, and then measured by Lamp and Rutherford. Its size is about 1 gigahertz. And the result of the first measurement was more or less in agreement with what Bethe computed. But Bethe also made some simplification, so his result is really, some people even say, accidentally correct. You see, the point is that he was doing calculations similar to ours, actually, but more sophisticated, sure. All the levels and no RWA and so on. But he decided to deal with this ultraviolet cutoff by setting it to some reasonable value. And he chose the cutoff for which the highest energy of photons accounted for were equal to the rest mass energy of the electron. And it happens so that the result is more or less okay. So that has been then criticized and done correctly by other people already using the full scale, full-blown relativistic theory. Okay, so this is not the end of the story, because with my approximation, with my alpha of z equal roughly 1 minus z naught, single pole approximation, I can use this and I can compute beta lambda. So in other words, I can compute spectrum of outgoing photons. Yes? And what is it? A spectrum of outgoing photons. Then I have to go back to what I have erased. If I know alpha, then I can plug it in, and the resulting equation I hope I have lambda divided by z minus z naught times z plus I omega lambda plus this omega 1, I now call it. So that's the solution for beta. And now, within the single pole approximation, my beta, for which I also want to go back to the position space, this fellow has got precisely 2 poles. One is my negative real part z naught, and the other is precisely on the imaginary axis. It is minus I omega lambda plus omega 1. Now, what does it mean? Well, it means that when I integrate, again close the integral the way I did before, are typically many other singularities somewhere far away. They die off quickly, but even this one is dying, but this one is not dying, because it's imaginary. So as time goes to infinity, for sufficiently long time, actually for time much longer than the lifetime of my excited state, I can approximate the result by just a residue at this pole. What is this? Well, this is, of course, gamma lambda divided by this fellow evaluated at this. So it is minus I omega lambda plus omega 1 minus z naught times e to minus I omega lambda minus omega 1, sorry, plus omega 1 times t. So, if I would like to know what's the probability of ejecting some particular photon lambda, then this is the square of this element. Yes. Now, the square of this element has a very simple structure, because what you get here is just omega lambda minus omega naught minus delta, where delta is this over infinite redshift square, plus gamma half squared, yes, and in the numerator I've got gamma lambda squared. What do we get? Well, we get Lorentzian line shape, yes. However, and that's the really definition, so to say, operational meaning of a lamp shift. However, maximum of my ejected spectrum is not exactly at the atomic transition frequency, but at the atomic frequency shifted or collected by this little collection coming from the interaction with a light field on the vacuum. Yes. Now, gamma, which just before was appearing as the decay constant for the decay of my excited state, now it pops up as the width of my Lorentzian line shape. And you probably know that indeed it's very hard to get back to so-called natural line, because typically in spectroscopy lines are broadened by many different mechanisms. For instance, by Doppler effect, and you have a lot of atoms and they travel. But if you would do a very precise slow atom experiment, then you should get close to this sort of expression. Now, this fellow squared is, of course, d times e lambda squared as before, and that tells us what is the angular distribution of the radiation that goes away. Yes. If I have my my d here, then if I would use epsilon in the direction of this d, what I want to say is, I don't want to dwell too much, that there is this H figure coming from this expression, which is well known, probably you know that such a donut-shaped radiation comes from the spontaneous emission. Now, I am done with the spontaneous emission, but I decided to make a remark about the scattering. And here is my remark about the scattering. How are we doing with time? Oh, it's plenty of time. Very good. So this remark that I want to make now is not in the printed notes, but I will give Rafał my notes written by hand. what I want to do, I want to do a problem for which in my initial state there is atom in the ground state and some photon of lambda 0. Now, within my Hamiltonian, of course, this fellow is again coupled directly only to the excited state. I was writing one here. Excited state as vacuum. But then this fellow is coupled again to all the possible lambdas. What does it mean? It means that if I start from here, I can end up with anything, and this anything that I can end up with is the result of the scattering, yes? If it's, say, photon going in a different direction. Are we able to solve this problem? Yes, not very difficult. Our equations are now having alpha without initial condition, I mean without non-zero initial condition, minus I omega 2 alpha minus I G lambda beta lambda sum over lambda. Now I have this one particular mode in which there is one photon. And for this mode I have to write this equation. Minus I omega 1 plus this omega 0, which is frequency of this particular incident mode. Of course, it makes sense to consider only near resonant scattering here. So omega naught of this photon that was here was very close again to the transition frequency. By the way, I want now to call omega A full atomic transition. So omega 2 minus omega 1 plus this delta, yes? This I will call omega A.
In the second equation we have omega 1 2 plus omega 1, yes?
Here?
Because you've changed the
No, omega 2 we have.
but in the second.
In the second is omega 1 plus omega 0, where omega 0 is the frequency of the shell. I know last night I decided I'm confusing slightly my notation, yes? Omega naught is popping up, but I hope you are smart guys. And all the remaining alpha not equal to this, lambda not equal to lambda 0, they have still beta lambda equal to minus I omega 1 plus omega lambda times beta lambda minus I G lambda beta, sorry, alpha. Now, this is also a set of very simple equations. Out of this fellow we compute beta naught. Out of this, all the remaining betas, plug them there. Yes, everything is again proportional to alpha, so that allows us to compute alpha. Yeah, and alpha, I will not go into too many details. You can find them in my notes, which I will distribute because I don't want to spend. I want to do two more things here today. So, I already computed the inverse transform for a long time. I get that alpha, which is, I remind you, the probability amplitude of absorbing the photon and staying up. It's minus I G naught divided by omega naught. That's the incident light minus omega A. That's from the single polar approximation again. minus gamma half, and I will be here. Sorry. And I also do this, okay? Times e to minus I omega naught plus omega 2 plus omega naught times t. Now, note that now alpha does not go to 0. In other words, the scattering problem that I set up is kind of sick because my incident photon is everywhere. And as the time progresses, of course there is some switch on effect which I omitted by doing single pole approximation of this imaginary pole again. But there is still non-zero amplitude, probability amplitude of absorbing photon and not emitting it. Yes. This is slightly, that makes the problem slightly uninteresting. But if we do this exercise to the very end, that helps to understand how to do the pulse scattering. What is pulse? Photon which has a form of a pulse? Well, it's some combination of these plane waves, yes, such that it vanishes outside of some big sphere or something. And then if we locate our wave packet, photon wave packet, single photon wave packet away from my system and allow it to pass through, then of course alpha will tend to 0. And then we have a proper scattering. Yes. Now, beta, I also computed. I will write now beta lambda. For lambda not equal to lambda 0. So, some other modes. Minus gamma lambda, g lambda is 0, divided by z minus z naught. That's my approximation for the resolver again. And now here are two imaginary poles, and that is trace of the fact that something is fishy here. And the fishy thing is that my incident, as I say, incident beam is all the time around times z plus I omega 1 plus omega 0. Now I have an expression with 3 single poles, and having them, this fellow, of course, contribution to this one is dying, so we don't care. But these two terms, of course, are both oscillating, and oscillating, of course, also forever, but with different frequencies. If omega lambda is not equal to omega 0. So this complication is a trace of the fact that our atom is always slightly excited. Had we done it properly with the wave packets, contribution from this fellow should also vanish, should also decrease in time. And what we should be left with is oscillation with this frequency, which is of course correct frequency of this state without any interaction. But this can happen only if my solution is for the problem in which photons finally separate from the atom. Yes? Only if photons are away, then they would acquire their own proper energy, which is omega lambda, which by assumption here is different than omega 0. But otherwise, the scheme that I have presented not only allows to compute the spectrum of spontaneous emission, but it also allows to look at the scattering processes, provided your initial state contains just one photon. Okay? All these remarks are especially directed towards you, Rafael. Yes, you are not a superior. Good. So my next remark is about effect which I understand most of you heard of, but I have to mention it here because it is related to the problem that we were solving. Namely, I want to tell you a little bit about what is called quantum zero effect. what is this ancient classic Zeno effect you remember? You know, paradox? Yes?
A rubber and a turtle.
Well, it's about the arrow, which at each point in time is somewhere. So how come it could be moving? If it's always somewhere. I think it is so silly. It's clear that he did not know the derivative, he did not know what velocity is, but nevertheless that's a classic paradox of Zeno.
Yeah.
Okay.
You always have to have a finite time to move in the finite.
Yes.
Finite.
Yes. Okay, but see, a catchy phrase, catchy name is a very good marketing strategy. It's been introduced to quantum physics by a very famous guy, by George Sudarshan, Indian physicist working in Texas for, I don't know, many decades, probably retired by now, and very famous guy, yes. And he, or maybe his student Mishra, who was the co-author of that paper, had this bright idea of calling the effect they discussed in the paper quantum Zeno effect. And everyone knows now something about quantum Zeno effect. What is it? Now, imagine that we've got some initial state, and imagine that we evolve it with some whatever complicated Hamiltonian. Imagine we project the result back on our initial state. Imagine we take a modulus of this fellow and square it. That's what should be called a survival probability. Yes? That's a probability of starting with something, letting it go, and then checking how much of the initial state is still there. Of course, our P of t equals E2 minus gamma t that we've got for spontaneous emission is just an example of such survival probability. Yes? It's a probability of starting with the excited atom in the vacuum and finding excited atom in the vacuum after time t, alpha squared. Yes? But if I take this fellow and if I put t equals 0 out of the very definition, what do I get? Well, I have to differentiate something like this. Yeah? So, and then of course I should say, should put t equal to 0, right? Okay, so when I differentiate this first guy, I will get minus I times Hamiltonian down. And if I set t equal to 0, then the exponential evolution equation will be gone. So out of this thing, at t equals 0, I will get minus I times psi Hamiltonian times psi. And what do I get here? Well, again, I get, differentiating this value, I get minus I times Hamiltonian. But since this is complex conjugate, then I have to write plus I h psi naught, psi naught. But Hamiltonian is a nice Hermitian operator, so I can plug it here. And then I see that I get 0. You agree? Now, if I take this fellow and do the derivative, take the derivative, then and put t equals 0, then it's minus gamma. So it's non-zero. So in other words, our approximation, the single polar approximation, by necessity must break down for very short times.
So where do we do this approximation?
Oh, we have done the single polar approximation to derive this. This is no approximation and no result, except that the derivative is equal to 0. Yeah. Well, let's go back to our z-plane and our lovely single pole, z0. h of this resolvent is a complicated function, whatever model we take, even the one that we had here with these two-level atoms. So it is fair to believe or to assume that there are other singularities. God knows how many, but some. But what we are certain is that they are placed or situated much farther away to the left than this dominant Wigner-Weisskopf pole or single pole. What does it mean? It means that if I have included these guys in my solution, then after short time which is inverse of the distance of this maybe closest other guy, these contributions will die, will be out, will be zero. And of course, for sufficiently long time, I will be left with my exponential decay. But from this beautiful trivial theorem that I've proved in one line, one thing is certain, namely that for very, very short times, when I should not dismiss contribution from these other guys, they add up to something that cancels linear term in the survival probability. So in other words, survival probability for very short times, must be 1 minus something times t squared, not something minus gamma t, for very short times. Well, people estimated this time for standard dipolar transitions in atoms, and it's incredibly short. It is, I don't know, 10 or 20 orders of magnitude shorter than the lifetime. So in other words, if I have my exponential decay curve, it's a huge exaggeration to say that it goes like this. But it does so, except that this distance here is incredibly tiny. It's incredibly tiny. Nevertheless, if I had a possibility of investigating, interrogating my atom, whether it has decayed or not, as often as this time scale of this contribution, then I would slow down the decay. Because, for instance, I measure it at this time. Probability that it has decayed, of course, is much lower than if I had used my exponential decay law. And then I find it not decay, and my decay process starts anew. So again goes quadratically. Then I check it. If it is still not decayed, then it goes this way again. And so on and so forth. In other words, if interrogated very often, my decay curve would turn into something like this. 1 minus alpha tiny delta t squared to the nth power, when delta t times n is my total time, yes? And this fellow could be much, if delta t is very small, could be much larger than e to minus gamma t. And that's exactly what Sudarshan called the quantum zero effect. Slowing down of the decay by frequent observations. Nobody has done it with decaying systems. Just because this interrogation time required is so incredibly short. But the theorem that it is zero is of course valid regardless whether this is a decay process or some other quantum mechanical evolution. And something which is studied very well with the resonant interaction of light with atom are Rabi oscillations. Yes. A situation, for instance, of the atom, two-level atom, in the cavity, and with the frequency here tuned to some particular mode in this cavity, and then one can arrange things in such a way that photon will be traded back and forth between this atom and the mode. This is called J.'s-Cummings model, and I don't want to do calculation of this thing here, because I believe everyone attended some class on quantum optics. You not, but everyone else heard about this Rabi flopping, yes? So this Rabi, what?
Oh, I heard about this, yes.
Of course you heard this. So what does it mean, this Rabi flopping? It means that if you would start, imagine such idealized situation, if you would start in the upper level and maybe n photons, then it will oscillate between these upper level and n photons and lower level and n plus 1 photons with some frequency which is called Rabi frequency. And the survival probability of staying still in the initial state goes like cosine of some omega t. Yes? Now this cosine, of course, developed into pi series for little t, as it should be, starts with t square in accordance with the general theorem. Yes? But now, this omega could be, anything could be, say, typically, I don't know, megahertz or something, and we would have for interrogation, we would have, I don't know, many nanoseconds, ages for the standard quantum optics measurements these days, yes. So it's only a question of interrogating this fellow, whether it is still in the upper level, and to interrogate Dave Wineland, another guy who got a Nobel Prize, by the way. Dave Wineland did the experiment in which there was another level and another light, and then was probing with short pulses whether this fellow is here. And indeed, he slowed down or almost stopped the Rabi oscillation this way. There was interesting discussion after this experiment was performed, whether it is really what's called quantum Zeno effect, or maybe something slightly different, because for some, there was some mystery of this quantum measurement involved in this Zeno effect. They were saying, and without mind or brain which is interacting with this fellow, could you really slow it? The guy who was my good friend, Axel Schenzle, he passed away 2 years ago. He wrote a beautiful paper about it, basically ridiculing those who had this idea, this idealistic idea that someone has to watch it to be really slowed down. He said, of course, interactions are enough. That interactions, quantum interactions, are in some sense in replacing this true measurement. And actually this is explanation why Wineland and Itano and several other co-workers in this famous paper indeed have seen this quantum Zeno effect. Probably many others did afterwards. How do I do with time? Oh, time is almost up. But I want to tell you something. I want to tell you that one can understand this quantum Zeno effect with purely classical example. Imagine we've got a completely classical linearly polarized beam. Okay? So here is this light polarized like this. And of course maybe this polarized just because it went across the polarizer maybe. Now imagine that we've got now a device which is allowing only tilted polarization to cross. Then of course we know that the probability of crossing, or rather intensity of the beam afterwards, is given by the cosine square of the angle between this polarization angle which is allowed and the initial polarization angle. And in particular, if alpha is 90 degrees, then of course nothing will come out. But imagine that between maybe some polarizing device here and this measurement here, I put something which is tilted by smaller angle. In principle, everyone would think, my goodness, if I just take a tilted device, then it never allows full beam to cross, full intensity. So perhaps if I have two attenuating devices, maybe less will come out. And as you know, of course, the result is that more will come out, yes. Because first, I will project on this alpha 1, and then on alpha 2 minus alpha 1, and this can be easily larger than cosine square of alpha. In particular, if I did thousands of these little guys tilted by little epsilon, then in the limit I will have everything passing through this guy. Yes? And that's the same mathematics as we have in the quantum Zener effect. I hope you like it. I like it very much. I have one more remark, but I think we have to stop here. I will only whet your appetite for the next lecture. Before I go to what I promised, theory of quantum open systems, I want to tell you about another anomaly of a decay process, namely the one that shows up at the very long times. It's called halving effect, or has been discovered in the 50s by Russian physicist Halfin, and also in some sense almost never, practically never observed. So I will tell you what it is and how we see very easily that some correction. One correction which we found was for very short times. I will show you how come there is also some corrections for incredibly long times.